Okay, let's begin chapter 6. And just to put things in perspective, in chapter 5 we did a lot of building things. Right? We looked at properties of exponents and what would happen if I multiplied things together. And then we looked at operations on polynomials, or what would happen if I multiplied two polynomials together. Chapter 6, right, is all revolved around doing that process in reverse. If I can multiply any two things together, I better be able to take them apart. Right? And that concept of taking things apart is called factoring. So, right, we're going to focus on factoring in chapter 6, and the first type of factoring that we have is removing the greatest common factor, or you might be more familiar with the term the GCF. So, let's get a little perspective here and do a quick little example, then I'll define what the GCF is in general. And if I gave you this problem and asked you to multiply, right, this wouldn't even belong in chapter 5. It's that. This is just pre-algebra. Can I get rid of parentheses by distributing? Certainly. Right? We can multiply. We know how to do this. 3 times 2x is 6x, and 3 times 5 is 15. Sure, we distributed. We finished. Right? But let's focus on what we did. We did multiply two things together. I took a monomial, this single 3, and I multiplied it by a binomial, this 2x plus 5. So I multiplied two expressions together, and I ended up with a result, 6x plus 15. So that's great. Right? And that's kind of like a chapter 5 thing to do, but in chapter 6, I want to decompose this. I want to look at this expression now and say, well, what two things did I have to multiply together to end up here? Right, so what we're going to do, our task is going to be to look at all the terms in an expression, doesn't matter how many there are, and we're going to find what they have in common. Right, in this case, we kind of already know the answer, but right, when we say what do they have in common, we're looking for a number that's going to divide evenly into all the terms. So that's our first goal, is to look at all the numbers or all the coefficients and decide what's the largest number that divides into 6 and 15. Well, the answer to that is 3. Right, once we pick out that 3 is the largest piece that divides into them, we open up a set of parentheses and we say, well, what's left over? If I divided all of these by 3, what would I have left? So 6x divided by 3 would be 2x. And 15 divided by 3 would be 5. Right, we're back to where we started. Right, so we undid this multiplication by finding this GCF. Right, so let me do a little more formal definition of the GCF. All right, there's going to be two parts to the greatest common factor. All right, the first part we're pretty adept at. We know our multiplication table. We're going to be very good at coming up with what that GCF is when we look at all the pieces. And we're not going to deal with large, super huge numbers. So we should be able to look at all the numbers in an expression and decide numerically what's the largest number that will divide evenly into every piece. So that's going to be the first part. So the numerical part. All right, we want the largest value that divides evenly into every term. We're accustomed to that. Right. The second piece is maybe new to you. You might have done it before, but it's going to work a little bit differently. The second case, we have to deal with our variables. All right, it's possible, right, for all the terms in an expression to share a variable. Right, in this case, that wasn't the case because this term had an x in it, but this term doesn't. So there's no x in common. But it's possible for all of the terms to share a common variable or common variables. Right, so when we're looking at the variables, the definition I'm going to use may not be the same as our working definition, but technically this is what we're looking for. We're looking for the largest power of each variable every term shares. Right, that's not technically the best working definition, right, but it is exactly what we're looking for. The largest power of each variable that every term shares. So I'll rewrite this. I'll do another working definition once we look at an example. Right, but that'll definitely work for a definition here. So let's look at, let's play a little game where I give you some terms and you identify what the GCF is amongst those terms. So if we just had 24, 32, and 16, right, the GCF between these three numerical terms, right, we're looking for the largest number, the largest value that divides evenly into every term. So the largest number that goes into all these, that will be 8. Right, 8 divides into 24, into 32, and into 16. Let's look at the variable situation. This is the one that's a little bit new, maybe a little bit weird. X to the 7th, X to the 4th, and X to the 8th. It's not going to work the same as our whole number pieces, as our kind of constant terms or coefficients. When we're dealing with variables, we have to look at the exponents, and we want to know how many x's can I say that each pile has in it. Okay. So when we're looking at variables, we want to find the highest power that they all have in common. So I can't say that they all have an x to the 8th in common, because this one doesn't have enough x's in order for me to say that. Neither does this one. Right. I can't say that they have x to the 7th in common. Right. This one does have 7 x's in it. This one has 7 x's in it, but this one does not. But x to the 4th is perfect, right? This term has 4 x's in it. Right? X to the 8th certainly has 4 x's in it, and x to the 7th certainly has 4 x's in it. All right, so when we're finding the GCF in terms of a variable, yeah, we want the largest power of the variable that every term shares. That's a good definition. But a better working definition is if I'm looking at all x terms, I'm going to pick the term that has the lowest exponent possible. If I use the lowest exponent, I can certainly say that this term has it in it, and all the other ones with higher exponents also have it in it. So my working definition is, that's a good start. Working definition would be the lowest visible power of each variable. Right? These two things are one and the same. The lowest power of each variable that I see is also the largest power that all of them share. So although these definitions may seem contradictory or opposite of each other, they both say the same thing. Whatever the lowest power is in this list of terms is the highest power that they all share. So let's do like a mix and match here with 15y to the 4th, 20y squared, and 25y to the 5th. Right, between these three terms, right, numerically, 15, 20, and 25, they have a common factor. They can all be reduced by or divided by 5. Right, and then we're dealing with y's. Look for the lowest power, y squared. I can take, right, this pile has 4 y's, this pile has 2 y's, and this pile has 5 y's. Well, I'm able to take 2 y's out of all these piles. So y squared, just look for the lowest exponent. Here's 3 other terms. And this will be my last example here, 14ab, 16a squared c, and 15a d to the 3rd. numerically, we want to find a number that divides into 14, 16, and 15. Well, if you think about that for a little bit, you're probably going to be hard-pressed to find any useful number that divides into 14 and 16 and 15. There's no good number that works. I mean, if you boil it down, yes, there is a number that works, and that number is 1. So like worst case scenario, you can always say that 1 is, but we say that's a trivial factor, because if I divide all of these by 1, it's not going to change them at all. So, and if there's nothing in common numerically, you don't have to write anything. Right, in terms of A's, right, the lowest amount of A's I see in any pile is just 1. So they certainly have a common factor of A. Right? Sometimes there's a common mistake to think just because I have B's or C's or D's in these terms that they have to be a part of my greatest common factor. But if I'm looking at B's, I want the lowest power of B in any term. Well, this one has B to the first, but there's no B's here and no B's here. I can't say that they have a B in common. So just because there's a B in the problem doesn't mean it's part of your GCF. Same go for C's. Right? No C's, no C's. Same go for D's. No D's, no D's. Right? So there's nothing else in common between all three of these terms besides the singular A. So you don't need to have a lot in common. Lots of expressions don't have anything in common. So this is hopefully trying to illustrate that you can have something just as small as just a single A in common. Or in fact, you could have nothing in common besides a 1. So we can find a GCF. All right, in our next video, we'll look at, well, once we know how to identify a GCF, right, how do we factor it out of an expression?